Headlines announce that NASA has found organics on Mars, as if we have finally discovered life. But in astrobiology, finding carbon, oxygen, and nitrogen is like finding flour and eggs in a kitchen. You have raw ingredients for a cake, but that doesn't guarantee a baker was ever there. Natural, non-biological processes can create an organic soup without a single living cell ever forming. To confirm a biological presence, scientists look for evidence of a process, something eating those ingredients and leaving physical traces behind. This search is the core mission of the Perseverance rover. For several years, it has been exploring Jezero Crater, an ancient, dried-up riverbed, selected specifically because its history of liquid water increases the odds of finding those traces. Finding these ingredients is a necessary first step, but it is no longer the finish line. Researchers now prioritize finding signs of metabolism, the chemical aftermath of a meal being consumed. While surveying a section of the riverbed, Perseverance reached a target named Cheyava Falls, a rock composed of ancient river sediments. Across the surface of this rock, the rover's cameras identified a peculiar visual feature: light-colored leopard spots, about a millimeter wide, each one surrounded by a dark, distinct ring. These spots provide a specific spatial arrangement for study, a physical pattern that mirrors the way microbes on Earth cluster together to process nutrients. The scientific method requires that every possible non-biological explanation be ruled out before life is considered. For the Cheyava Falls discovery to hold up, researchers must show that no known geological process could have created these spots. Perseverance analyzed the chemistry of these spots and found a concentrated mix of organic molecules and two specific iron minerals, vivianite and gregite. On Earth, this combination is recognized as a chemical byproduct of life. Microbes consume organics for energy and excrete iron minerals as waste, leaving a signature in the rock. Their localized arrangement suggests whatever created them stayed in one place to work. This convergence of chemical and physical data provides a strong lead for an ancient biological signature, but the discovery must now survive a series of geological tests. The team tested alternatives. First, could extreme heat or pressure forge these deposits? Data shows they formed in low-temperature liquid water, never reaching volcanic temperatures. Second, could acidic reactions etch these spots? The surrounding minerals show no extreme acidity. Both abiotic pathways are removed. By systematically ruling out common geological explanations, the biological hypothesis remains the most consistent explanation for the data Perseverance has gathered so far. Even if microbes once lived in this riverbed, the surface of modern Mars is a wasteland. Lethal cosmic and UV radiation have spent billions of years stripping away the atmosphere and destroying any surface DNA. However, as you move deeper into the crust, the planet's internal heat creates a different environment. Away from surface radiation, temperatures rise. We know Mars contains vast reservoirs of water ice. In these deeper, warmer zones, physics suggests liquid water aquifers should exist beneath the surface. If life once thrived on the surface, providing a stronger rationale to search these deep niches. It suggests that as the surface became uninhabitable, life may have followed the water downward into protected underground outposts. The era when these microbes were potentially active was a time of violent change. The early solar system was thick with debris, and massive asteroid impacts on Mars on the surface were frequent and incredibly powerful. These impacts were strong enough to blast Martian rocks into space. We have found dozens of these rocks on Earth, proving that material has been traveling between our two planets for billions of years. This raises the question of whether a microbe could survive the vacuum and radiation of an interplanetary journey. It seems unlikely, until we look at the extremes life can endure. Earth's own tardigrades can survive the vacuum of space and massive doses of radiation. Their resilience demonstrates that biological organisms are capable of surviving the conditions required for a trip from Mars to Earth. The discovery at Cheyava Falls validates the strategy of searching ancient river deltas. It brings us closer to determining if life emerged independently on Mars, or if our world's history is linked to the one next door.